Good morning or good afternoon, everybody. My name is Antoine Glorieux, and I'm working at ArcelorMittal R&D in Luxembourg. I'm very happy to be here and to present you the simplified design method for stiffened cellular beams against web post buckling. So here is the content of the presentation. So first we will go through an introduction where I will present you the main failure mode of cellular beams and then our solution to prevent web post buckling. Then we will go through numerical simulation we did to assess the efficiency of such a stiffener, and then through the analytical method we developed to calculate the resistance of this stiffener, and then I will present you some cases of optimization we did, and finally the conclusions. So here are the two additional main failure modes we have to consider for cellular beams or beams with web openings. The first one, as you can see here, is the Virendel mechanism, and the second one is web post buckling, which is the focus of this presentation. The solution we propose to prevent web post buckling is to weld a plate section or U section perpendicularly to the web. Just a parenthesis, this study is not focused on web post buckling due to point load on top of it, but on web post buckling due to internal forces due to global loading, such as distributed loading, for example. A couple of assumptions here. So the web post doesn't have to be the same height of the web and then doesn't have to be welded to the flanges, but as you can see here on the deformed shape, it should be at least as high as the opening diameter to really prevent the buckling. Concerning the numerical simulations, so the software we used was Saphir, and we modeled the beam using shell element and the material steel EC3 2D. Concerning the boundary condition, the beams are simply supported, and as you can see here, the lateral torsional buckling is blocked. And the loading was used using F1PS function, so it means that the loading increases with time until the failure of the beam is reached. So here it's a distributed load on the top flange, but we tried medi loads such as also point loads. And last point is the deformed shape we imposed to the web. So it's equals to 0.0025 times the height of the web for the sine curve amplitude. The results we obtain in terms of displacement. So here I'm presenting you a case with an IPE 600, and here you have the dimension of the opening end of the web post. And here is the out of plane displacement of the beam, and you can see that clearly that you have a web post buckling failure. Just something I forgot to mention, here you can see that the end post is stiffened to prevent local failure mode due to support reactions. And here you have the second model with the two first web posts stiffened, and you can clearly see that the out of plane displacement is blocked, and we have much more displacement on the third web post, which fails by buckling. Concerning the stresses analysis, so we analyzed von Mises stresses in the web post, and here you can see, so you have on the top left corner the numbering of the elements and the corresponding von Mises stresses in this element. It's for S460 steel grade, so you can see for the 1 and the 7 it's almost plastified, but for the other one it doesn't. So it means that we have failure due to an instability. And here is the same beam, but with stiffened web post. So this is again the first web post, and we can see that we can reach for almost all the elements, and except maybe the one in the middle, the plastic capacity of the web post, meaning that the stiffener is efficient to prevent buckling. If we go through analytical verifications, 3 of them are performed to verify the web post resistance. So the first one is buckling, then shear, then bending. So just a small parenthesis, 2 methods are described in Eurocode 3.1.13, one in the core of the text, if I may say, and another one which is an alternative method. The alternative one, it's a bit more complicated, but also a bit more optimized, and we advise to use it if you want to have the most optimized design for a stiffened web post. And we adapted the, if I may say, most simple one for the stiffened web post. So how we did that? We considered the stiffener in the calculation of the slenderness of the web post. So here you can see the calculation formula of the slenderness of an unstiffened web post. So it corresponds to this buckling length. It's the diagonal in red. And we took exactly the same assumption considering the stiffener area and the inertia brought by the stiffener to the web post buckling. So it's exactly the same formula, but instead of putting the inertia of the web post, we replace it by IS, which is the inertia of the stiffened web post. And then we just calculate the psi factor, and we obtain the buckling resistance multiplying this psi factor with the yield strength and the web post area, to be compared with the normal forces acting on the web post. Concerning shear, I don't spend a lot of time in this. We decided to neglect the contribution of the stiffener in shear resistance, so it's calculated classically. So analyzing numerical simulation, it appeared that the main failure of a stiffened web post was bending of the critical section. And in Eurocode 1.3.1.13, sorry, the verification is only performed in the middle of the web post. So I will show you how we perform this verification. The critical section is a section for which the ratio resistance divided by solicitation is the lowest. So you can see it here on, it's the orange line in the drawing, and on the graphs here on the right you can see the evolution in orange of the bending moment, which is basically the horizontal shear force acting the web post times the lever arm. And in blue you can see the evolution of the resistance, and you can see that at some point both lines are crossing. It means that this is the position of the critical section, and you can find it analytically with those two formulas. The bending resistance of the web post is calculated considering plastic design for class 1 and 2 and elastic design for class 3, knowing that the classification of the web post is performed considering Virendell assumption for the classification as described in Eurocode 3.1.13. For class 4 section, the web post width is reduced to its limiting value to be in class 3 and calculated considering elastic design. The shear interaction is considered with the Fy effective, and the obtained resistance is compared to the bending moment soliciting in the critical section. And one thing we should mention is that this bending resistance is increased by this K factor, which is the post-critical factor, to take into account the fact that the failure of the web post doesn't imply the whole failure of the beam. This graph summarizes the numerical simulations we performed in comparison to the analytical methods. So we can see that the analytical method provides a margin located between 10 and 20%. Concerning optimization, we will see a couple of examples to assess the interest of such a stiffener in the design of the beam. So for this example, we have a 12-meter beam S460, and the targeted bearing capacity is 90 kilonewton per meter, and the opening dimension and the web post width are fixed. So here is the first solution with an HEA 650, and we see that we do not reach the bearing capacity target. But now if we take the same beam and just weld 4 stiffener, by 4 stiffener I mean 2 at each end of the beam, we can increase the bearing capacity to 90.4 kilonewton per meter, which corresponds to 27% increase. Another solution would be to increase the steel profile to HEB 650, and we can see that we can also increase the bearing capacity above 90 kilonewton per meter, but the prices increases significantly. Another solution with another steel profile, HEA 700, we can see also that we are a bit below the 90 kilonewton per meter we targeted, but here the main disadvantage is the height, which increased significantly, which might be not suitable for the project. So here is another example, considering a 10-meter beam with a targeted bearing capacity of 55 kilonewton per meter. Again, the opening diameter and the web post widths are fixed, but now we have no constraint on the steel grade. So the first solution proposed is an IPE 500 S355, and we can see that we do not reach the targeted bearing capacity. So next solution is the same beam but with 4 web post stiffeners. Again, it's 2 at each end of the beam, and we can see that we increase the bearing capacity up to 61.2 kilonewton per meter, which corresponds to a 25% increase. Again, the same beam, but this time we increase the steel grade up to S460, and we can see that we have a bit less than the beam with 4 stiffness, S355, but we are still above 55 kilonewton per meter, and the cost is more interesting considering this assumption that the S355 is less expensive by 14 euros per ton than the S460. And here the last example of a 12-meter beam with S460, and this is more focused on the height. So the targeted loading is 40 kilonewton per meter, and again the opening dimension and the web post widths are fixed. And this table just shows you how is it possible to reduce the height of the beam with the same price and the same bearing capacity. So just by welding stiffener, again, this is same assumption, the number corresponds to the full number of stiffeners of the beam. You can reduce up to 25% the beam height. So we are now to the conclusion, and we can say that the web post stiffener really prevent the web post buckling, and the analytical method which is proposed matches the numerical results. And here you have a small table of some simulation we performed, and depending on the configuration and how far are the other failure mode, we can go up to more than 30% increase in terms of bearing capacity. Thank you for your attention, and questions are very welcome.